So if we look at these magnets, we know that magnets can interact with each other over a distance. We know that opposite poles are going to attract, and we know that like poles are going to repel each other. Now, why does that happen? Well, we can look at the space between them and see what's going on in terms of those electric fields. So we see that if we're between these magnets, you see that that compass needle points out from the north pole of this magnet and into the south of that magnet. And if I were to put compass needles at different points, we start to see a general rule, where in both of these situations, the compass needle points out from the north pole of the magnet and towards the south pole of the magnet. What these compass needles are doing is they are following the field lines between those two magnets. If I were to quickly move these out of the way, we see that the magnetic field between these is out from north towards south. And these field lines also interact between the poles on the same magnet. So we go out from north towards south. This is the direction that a compass needle points. A compass needle is how we define a magnetic field. And because compasses are tiny magnets, they will repel north and be attracted to south. Now we can also see what happens if we have two poles towards each other. Let's see what that repulsion looks like. So now I take maybe these two north poles, and we'll see what these field lines look like. So you'll notice that in between, it's actually going someplace different than before. It's still going out from north. But now, because those field lines are repelling each other, we end up with something looking like this in between. So if we were to draw these field lines, again, they're going to be out from north, but they're going to be repelling and towards south. So if I were to draw these field lines at these different points, they would be out from the north pole of the magnet and towards the south pole of the magnet. So we use a compass to define the direction of a magnetic field. So just like electric and gravitational fields explain how the electric force and gravitational force acts over a distance, the magnetic field explains how magnetism acts over a distance as well. And again, the way that we define it, so the way that we define a magnetic field, the direction, is where a compass needle would point. So a compass is our tool for defining magnetic fields. And we know that if we point a compass, it will be out from north and towards the south pole of the magnet. So out from north towards south is where a compass needle would point. Now this has some implications for the Earth, because I know if I stand with the compass here, in, I guess that's Mexico, it's going to point towards the North Pole. Now, what I know now, based off of how we define the direction of a magnetic field, that would be the magnetic South Pole. So compass needles, again, point out from north and towards south. So up here in the geographic North Pole is actually the magnetic South Pole. So there is a difference between the magnetic poles and the geographic poles. Geographic poles are based off of maps, and the North Pole, where Santa Claus lives, is the geographic North Pole. But using our definition of a compass, the geographic North Pole is actually the magnetic South. Now, Earth's magnetic field has some important properties. So the magnetic field is really important to help protect us from solar flares. We have all these different particles coming from the sun. So we have like different forms of radiation and different very fast particles that are ejected off of the sun, and they come flying at the Earth. What happens when they get up in this in Earth's magnetic field is the magnetic field will actually trap these particles, so it will deflect them, and then it will trap them in these polar regions. And as they're trapped, so we have charges, like maybe like an electron or other particles like that. So it's trapped and it starts to move in a circle. And as it's moving in a circle, anything that changes its direction in physics, we say that it accelerates. So because it's moving in a circle, we have an accelerating charge. It ends up emitting different wavelengths of light. And that's what the northern lights are. The northern lights are those charges coming from the sun that are trapped in the Earth's magnetic field and then accelerated in the polar regions. The magnetic poles are also moving, so they're not in the same place as they used to. So it's actually moving away from Canada towards Siberia. And according to recent data, it's happening at an ever-increasing rate. So to summarize these three types of fields, so an electric field is described as, we describe it using a positive chest charge. So where would a positive charge go? The sources for this field are things with charge. And so when we look at this field around a positive charge, it's out. And around a negative charge, it's toward. Gravitational field we looked at last time too, that's anything with mass. And we describe that as the direction an object with mass accelerates. So on the surface of the Earth, or I guess around the Earth, so here's our Earth, we have a gravitational field and it's towards the center of the Earth, and that's what we were looking at last week. In order to have a magnetic field, we actually need a moving charge. If we have a moving charge, we'll have a magnetic field. And magnets have moving charge, like permanent magnets. They're just on the atomic scale. So we use a compass to define a magnetic field, and we know that it's out from north. So it'll be out from the north pole of a magnet, and it will be into the south pole of anything that's magnetic. So that's how we define and describe these three types of fields. The last thing we're going to talk about this week is going to be a motor. So a motor can kind of use this idea. It can use the idea of moving charge. So if we have moving charge, like through a wire, we can produce a magnetic field. And if we put that in another magnetic field, so like here we have a permanent magnet, if we put that in another magnetic field, those magnets can interact, and that repulsion or that attraction can cause some movement. And that's what a motor is. So we have a battery here. This is where we get the charge. The charge moves through this copper wire. So this copper wire has charge moving through it, and it produces its own magnetic field. So electrons move through it, and it interacts with this permanent magnet. So a wire loop or a wire coil is important. A permanent magnet is important. We also have brushes, and there's this thing called a commutator. A commutator has a break in it. So what would happen if we didn't have a break is this coil would just deflect and then get stuck. It wouldn't deflect any further. It would go at an angle, and then it would stick there. That break allows the current to actually shut off. So this motor is actually, the current is going. There's a circuit, then it's off. Circuit off. Every time it hits that break, it turns off. And that allows it to keep traveling in the same direction. Because when we have a motor, we probably want it to rotate the same way all the time. We don't want it to constantly be switching direction. That's what we're going to look at next week when we look at alternating current. So we want it continuously going in a circle, and that's what that commutator is for. That's why that brake is important. Here's a really simple motor you can build just using simple parts. So there's a power supply, so we need moving current. That current needs to be moving through an external wire. That's what this is. We need a loop of wire, so there's that shape. And we also need another magnet, so an external magnet, and that's what these are down here. So this is called just a homopolar motor because it's got just one pole. If I take this and I were to put it on top there, well, I guess the poles don't change, that's why. So now I've completed the circuit. It's getting a little hot on the fingers. But if I were to let go of it, it's going to start to move. So now those magnetic fields interact and I end up with a motor. Now if I could get this balanced better, which takes a little bit of time, but you kind of get the idea that if we have a complete circuit, so it only works when these brushes, as you could call these brushes, are touching the magnet. The circuit needs to be completed through the wire, and then the magnetic field induced here interacts with this magnetic field, and it causes it to move.